Mr. Minnick here, helping my AP students with the multiple choice questions on the year 2010 course description practice exam. Number one, we see the answer is B, now that I have the answer key handy. And to do a problem like this, there's a lot of loop tracing on the exam. And you need to know how to trace loops, but you don't have to trace the whole loop exhaustively. So you start things out and you use the scratch paper, the margin provided here. K starts at 0. Already we're stuck. What in the heck is 0 mod 3? It's easy to do 10 mod 3. And you just take 10 divided by 3, and the remainder there, 3 times 3 is 9. You do subtraction. The remainder is 1, and that's how you do 10 mod 3. Well, if you ever get to a situation where you need to take a little number modded by a big number, well, you just put the little number in there where originally you had the big number. And you still take the 3 in this case and you divide it into that. So I'm pretty much redoing this with a 0 plugged in there instead of a 10. And 3 goes into 0 0 times. 0 times 3 is 0. You do the subtraction and you get a remainder of 0. So this right here simplifies to 0. Is 0 equal to 1? False. So we didn't even have to do that. Well, that was just k being 0. Now we come back up and we iterate the loop again. We come in from the right side and we add 2 to k, not 1. This is not k++. And now we keep going. Hey, what's 2 mod 3? Well, you could do all this scratch work again, but the rule is when you have a little number modded by a bigger number, it always comes out to that the answer, the remainder, is always the little number. That 0 is the answer because it was the little number. So this simplifies to 2, and 2 is not equal to 1, so it's still false. We don't do anything yet. K bumps up to 4, and now we start to see some action here. When k is 4, we're asking the question, what's 4 mod 3? And 4 mod 3, well, it ends up being the remainder of 1. Bingo, we have a true, which means we do this. K is currently 4, so my first little piece of output is a 4. And there's a little blank space concatenated there. So I know my answer is either A or B with just a little bit of tracing. We're not up to this 20 yet, but at least I have a fighting chance of guessing one or the other. If you kept going with this, you would see that a 10 prints next and the answer ends up being B. Don't keep tracing to the end of the loop. We're trying to save time here. Okay, question number 2. A good old array list question. Well, the array list starts from nothingness. It has a size of 0. We add a P onto it. We add the letter Q into this array list. I'm not going to take time always to draw my little boxes, but you can keep track of this however you want to on the day of the AP exam. The R gets added to the end because that's how the add method works. It tacks things on to the end. Then you have to know what the set does. Well, keep in mind that on your cheat sheet, the quick reference, it will explain what the set method does, but you should know. It puts an S, a lowercase s, in position 2 of this array list. And position 2 is where the R currently is. So this lowercase s overwrites the uppercase R. And now the add method, when it has 2 parameters, it works a little differently than it did here. It does not tack the T onto the end. It inserts the T into position 2. So here's position 2 that now has a capital T. That S shifts to the right, so it's now in the newly created position 3. And now we do an add U. The U ends up being added to the tail end. And this right here is the final answer, which according to the answer key should be C, and we do have a match. That was considered to be an easy question on the AP exam. Okay, going to the next page of this test. Question number 3. I'm telling you right now that the answer is E. And this is a very famous logic problem. we have this list right here of numbers. Let's put their position numbers here. And better yet, let's rewrite it, because this is the kind of question that you just need to trace it to really be comfortable that you know the answer. So we've got an array list of size whatever. We number these things from 0 up. Okay, it has a size of 8, and the positions are 0 through 7. And we follow this algorithm. We have a local variable k that begins its life at 0. And we have this weirdly named variable named 0. The name of the variable is 0. It's not an int, it's an integer, which is pretty much the same thing. You can think of it as being equal to 0, because it is. And now we trace this loop. That's where all the fun is. Is k less than nums.size? Well, currently the size of this is 8. So make a little note that the size is currently 8, and k is 0, and 0 is less than 8, so we do go through the loop. If, what the heck, dot, dot, parenthesis, let's follow the order of operations here. What is k right now? Well, k is 0. What do you do when you do a dot get 0? Well, you get what's in position 0, which coincidentally is another 0. So this right here simplifies to a 0. It's technically an integer object 0 and not an int. Oh well. Is 0 dot equal to 0? Well, 0 is currently 0. So this 0 is equal to that 0. So we do indeed execute this remove statement. And how does remove work? Well, because k is currently 0, we are removing whatever's stored in position 0 here. So this is getting removed. And when you remove something in an array list, everything shifts forward 1. So take the time to write this out. Let's be sure of getting certain ones right on the AP exam that you should be confident of. So all of those now are overwritten with these entries. And there is no position 7 anymore. So we k++, k bumps up to 1. We hit this curly brace. We come back up to the top of the while loop. And the size is reevaluated to be a 7. The size is now 7, not 8 anymore. Is k less than that? Yeah, 1 is less than 7. So now we get to do this fun again. We need to analyze this if statement. And the if statement is telling us to do a get of k. Well, k is 1. And if we do that get, that means we're getting this 4, because it's in position 1 currently. Is 4 equal to 0, which I accidentally erased here? No, it's not. This 4 is not equal to that 0. So this is false. Nothing gets removed. That's a bummer. But we still k++, at least, because that is not in a set of curly braces. That is not part of the if. And even if it were indented, it would not be part of the if, because the programmer did not use curly braces here. So it's only this one line of code that's part of the if. Anyway, k++, it's up to 2. We loop back up to the top. We say, hey, what's the size of nums? It's still 7. K is still less than 7. So we do go through this loop again. Stop the press. Look at what we currently have. We have k is ++ up to 2. So all the action is going to happen over here. If there is any more removing to be done, it's going to be removing this stuff. And quite obviously by now, you should have realized it, it looks like this algorithm is trying to remove these zeros. But this 0 is like squeezed in. It's in there. It's in the final answer. It will not be removed. B is so wrong, but so many kids in the country will answer B. Trust me. If you get this problem right, if you say E instead of B, you are one of the few kids in this country who will someday work for a good company like Google, Microsoft, Apple, because you can trace code. Or you might even be a surgeon someday, operating on a, well, me. I would trust you if you can get this kind of a question right. I will write a recommendation for you to go to med school, a good med school. Because these two zeros were next to each other, and because the k++ is sort of bad code, it skips over this 0 right here. This never gets removed. Moving on now to the next page of this practice exam. We have a good old Roman numeral question where you have to eliminate answers and all that stuff. The answer to number 4, you can already probably see on the answer key that I provided you. It's D. So Roman numerals 1 and 3 apparently work, but Roman numeral 2, well, guess why it doesn't work? Because this is a squiggly underlined compile error in a program like Eclipse. You can't do that. You needed to do 84 less than or equal to score, and symbol, score less than or equal to 92. That's the way it has to be coded. It's just a straight compile error. Roman numerals 1 and 3 apparently do work. You can trace that code. It's pretty easy. Okay, moving on to this one. This is a hard problem, but once you see patterns, you'll get one right like this. And there will be one probably on the real AP exam this year like this. They're all double nested for loops. And what happens, we did a former worksheet on this. J iterates 5 times because it goes 1 plus 1. And J kind of think of that as your rows, and think of K, the inner loop, as your columns. Because of the way we have a concatenated space here, and outside of this for loop, but inside of this for loop, we have a lonely print ln. That brings you down to the next line. This code, if it were to execute, would print an arrangement of 5 numbers on 5 different lines. A nice little square it would print. That is not what we want. So this is ruled out, even without tracing all of this. Do you really think that they want you to trace all of these code segments? You don't have time for that. You need to see patterns. Again, if you can get this one right, I give you permission to operate on me someday, should it be necessary. Okay, well anyway, this is like a square. That is not what we want as output. That's out. What other one can we rule out because it's a square? None of them, unfortunately. I can already tell what I'm looking at. Now see how we have a J here instead of a 5? That means that this one is triangular. But is it this triangle pattern? Is it this triangle? Is it this triangle? No, that was already repeated. Anyway, just trust me. There are like 4 different triangles we could have here. And which one is this? Which triangular pattern is this because of the use of... Oh, no. This one is a square. I can tell here because of the 5 and the 1. This is a square. It just goes from like right to left, top down, instead of the other way. So that is a square. That's ruled out. At least now you have a fighting chance of guessing between B, D, and C, E. And anyway, if you just trace this a little tiny bit, you will soon see that the answer here, the answer to this problem, number 5, is D. So you really don't have to trace it too far in the algorithm with this J plugged in as a 1. You'll see that right away there's only one number printed on the first line. It immediately drops down to the next line and begins to print the triangular pattern. Whoops, sorry about that. I was completely wrong. Because J is 1, it does print 5, 4, 3, 2, 1 on that first line. Sorry, I looked at that wrong. So you do have a full row of 5 numbers there, but then because J bumps up to 2, and because of the way this goes from 5 down to 2, we end up with only 4 numbers on the next line. So we begin the pattern of the triangle that is being called for here. Okay, you can always put this in Eclipse and copy and paste it and see what it does if you don't trust me or the answer key. Number 6. This is the kind of question that hopefully it's theory. You'll get it right. The answer was A. Okay, this kind of a question is object-oriented design, OOD we call it. Should you have 4 separate classes? No. That defeats the whole purpose of ISA relationships and HASA composition. Inheritance and composition would be put into Java unnecessarily if B was the answer. We don't like unrelated stuff. Well, should car be a parent class and then have doors below it and AC below it and miles per gallon? In other words, would you say that door is a car? Because when you draw inheritance charts, the thing below, the child, is a parent. That makes no sense. Air conditioner is a car. That is so wrong. A subclass is just a fancy way of saying a child class. You should know that it was vocabulary. Number D, letter D. No. Doors should not be a subclass of car, so right away, that much into it, you know that D is also stupid. And E. Should these have car as a child? You can't do that in Java. You can't have a parent, more than one parent. Whoops, I drew the arrow the wrong way. You can't have a class have as its parents 3 classes. It doesn't allow multiple inheritance in Java. It does in some other languages, but that's just illegal. So I'm left with A, which so obviously was the right way to do it. Because air conditioning should be like a true or false feature of whether the car has air conditioning. Miles per gallon is like a number. It's expressed to the nearest decimal number for accuracy. So A is clearly the answer. Number 7, you should know about the famous interface called comparable. The answer to number 7 is A. So apparently this signature right here is the one that you would use. And actually, that is just the law. When we studied the the comparable method, and specifically the compared to method, the comparable class with the compared to method, you always have to use this as your header for the compared to method. Now you can use X instead of other, but you have to have the word object there. It's just the way it is. That's the law. So that is so easy. Number 7A, if anybody got that wrong, shame on you. This next question has to do with this class called type record. Skim the code on this page of the booklet, and then of course read the question, number 8, that pertains to that code, and fill in the necessary logic to the missing code area. So the answer is C. If you study this code and take the short minute that would take to analyze it, you would see that a time record is really just an object that has an hours and a number of minutes. And let's say that you have 1 hour stored there and 30 minutes in these two properties of this class time record. You have a normal accessor method for hours and an accessor method for minutes. But what you're being asked to do in number 8 is to supply this missing code. Well, if somebody has already told you that you have an object that's storing 1 hour and 30 minutes, and they're adding to that, let's say 2 hours, and let's just say 45 minutes, how do you come up with the total number of hours and minutes? Well, by taking an hour and 30 and adding to that 2 hours and 45 minutes, you see that the hour portions, 1 plus 2, adds up to 3 total hours. And that's what we have here. We end up with 3 hours. So that's good so far. That code is working for us. And the number of minutes, 30 plus 45, well, that unfortunately adds up here to 75 minutes. And we can't say that the answer is 3 hours and 75 minutes. We have to mod. We have to divide the number of minutes by 60 and find the remainder. You know, that's what you do normally. You take 75 and you divide it by 60, and you find out that the remainder of that long division is 15 minutes. Now what do you do with this 1? You take this 1 and you add it into the 3 to bump up your total number of hours to 4. Then the leftover minutes, this remainder, is what you write here. So in other words, this plus this does not equal this. It actually equals this. This is the incorrect way to represent it. We can't go around saying 75 minutes. So how do we do that in code? Well, by looking at the options that are provided to us on this page, we see that this is the only solution that does that. Because when you take the number of minutes and divide it by 60, 75 divided by 60. In Java, when you have an integer divided by an integer, you chop off the decimal places. So this is actually equal to 1. And that 1 is being added into the previous number of hours, which I believe was a 3, if you look back in this video. So for a grand total of 4 hours, and that's what we want. Then the number of minutes that we had accumulated on the previous page, that 75 modulus 60 leaves a remainder of 15 minutes. Perfect. We have updated the hours and minutes instance variables with what they needed to be to represent a time record of 4 hours and 15 minutes. None of these other ones come close to working. Well, maybe close, but they don't work. C works. For the AP exam, please review MOD, and especially in the context of working with time. 60 minutes in an hour, 24 hours in a day. That's called clock arithmetic, and it makes use of modulus, or the mod operator. Number 9, that's a pretty tricky question on this practice exam. Number 9 involves an array, and it's an array of time record objects. Time record objects. Maybe on the exam you draw a little picture, a diagram rather, of an array, and the length of the array is 100, so this would be position 99, position 0, 1, 2, etc., ... And in each position of the array is a time record object with 0 hours and 0 minutes. So maybe I represent that as a little object that's stored in position 0 of the array. Now the array is named total. I'm sorry, the array is named time cards. And within these 100 positions of the array, we have these time record objects. More about those later. Okay, analyzing this code. Well, total is one individual time record object that has a number of hours and minutes in it. Just like each of these elements have a number of hours and minutes stored in each little square there that I've made. And what is this loop doing? It's adding up all of those time records. And we're using this as the variable that's totaling all of these up. Now this is not an int. This is a time record object that within it, it has an int for hours and an int for minutes. So which of these pieces of code does what the advanced method, which one which of these code segments, just fills in this blank right here? Well, what are we trying to do according to this paragraph? We're trying to go through all of these time cards and add them up into one grand total here. So we are going to the length of this array, which is 100, k less than 100. We're k plus plusing, so we are going array position by array position through this for loop. The for loop's okay. And which of these code segments fulfills that task? The answer ends up being D. You can eliminate C even if you don't understand any more of the problem, because hours and minutes are private if you go look at the previous page. And this code segment is probably in a client program. It is actually. It probably is in a client program, so that's generally not allowed. Now this code is using get hours, but so is this. And this code does it without using get hours, it uses advanced. Well, the key here is that you call the advance method on total. So this variable right here is your variable called total. And when you do a dot advance, it takes some number of hours and minutes. Perhaps this is 1 hour and 45 minutes. It gets added in here, so this running total, and then we k++ to here, and let's pretend that this is, I'm just going to pretend that this is 4 hours and 15 minutes. No, I'm sorry, from the previous example, let's just pretend that that is whatever we were doing in that previous problem. An hour and 30 minutes, I believe it was. Let's pretend that that's an hour and 30 minutes. Well, by taking an hour and 30 minutes and sending that as the parameter h and 30 as the parameter m to the advanced method that we previously talked about up here, this 1 gets added to that 1 for a grand total of 2. This 30 gets added to that 45, but because that adds up to 75, 1 more hour is added to the hours portion, and there's a leftover 15 minutes. So 1 hour and 30 minutes added into the previous, and we end up with 4 hours, whatever I just said there in the video, 2 hours and 15 minutes does successfully add. This answer D is the code that you need to pull the 1 out of here. All of this is just a 1, and the 45 gets pulled out of here. And so in other words, we have advance parentheses 1 comma 45 that's being added to 0 0. Then when we k++, the 130 here gets sent to the advanced method, and the 1 and the 30 get added into this running total, and so on. None of these other code segments are properly calling the method advance or logically adding up the total in the right variable called total. Moving on to the next question on this practice exam. Number 10, the answer according to the answer key is A. And this is hard. One way to do this, although it might be a bit of a time sink, would be to create a little array of a decent length, plug some numbers in. In this case, the numbers are sorted. So just make up some numbers that are in sorted order, put them in your array with index positions, and notice that this method mystery is recursive, a little tricky. So the method calls itself. So we are in stack frame number 1. In stack frame number 1, the way I taught you to do recursion, this parameter 0 plugs in for low. So in stack frame number 1, low is the value 0, and the parameter high is whatever this middle parameter is, array length minus 1. The length of this array is 5. 5 minus 1 is 4. So 4 is passed up as high in this first stack frame. Then num is this value. You're allowed to make up any num that you want. According to the precondition, num can pretty much be anything. I'm just going to plug in a num of, say, 9 for my first, for the sample. So in stack frame 1, that's what happens. Now let's trace the code. What is mid? Well, mid's a local variable. It also exists in stack frame number 1. And mid is simply low plus high divided by 2. 4 divided by 2 is 2. And is low greater than high? No, it's not. Is array mid less than num? Well, mid is 2, and ARR2 would be 8. So we're asking, is 8 less than num? And num is currently 9. Well, yes it is. Now this was a number I just arbitrarily made up, this 9. But since that's true, we now have to return whatever this is. In other words, we drill down to stack frame number 2, and we're calling the mystery method all over again, but this time the first parameter is mid plus 1. This mid, 2, plus 1 is 3, and it's the first parameter, so it plugs in for low. So in stack frame number 2, low would be 3. High remains the same value that it was up in stack frame 1, and num also stays the same. Now that we're executing in stack frame number 2, we reevaluate mid. Mid is whatever low plus high divided by 2 is. 3 plus 4 is 7. 7 divided by 2 is 3. Don't say 3.5. It's integer division here, 3. Okay, we're not done yet. We have to analyze this if-else-if statement. Is low in stack frame 2, is low greater than high? No, it's not. Is ARR mid less than num? Well, those were numbers from a previous stack frame. Let's see, mid is 3. That would take us to the number 10. We're really asking here, is 10 less than num? And num is 9. No, it's not. This is a false. So we come down here. Is 10 greater than num? Yes, it is. 10 is greater than 9. So we now make it to a third stack frame. Hopefully you see a pattern here, but you might not. This kind of a question takes a long time, and if you can't just answer it by ruling out a couple and moving on, maybe you want to save this for later in the exam if you have extra time. Anyway, I'm going to move forward here. Low in this recursive case is 3. 3 plugs in, so low doesn't change at all. High in this new stack frame is whatever mid minus 1 was from before. So 3 minus 1 is 2. And num stays the same. And we now recalculate mid in this new stack frame. And mid is low plus high divided by 2. 3 plus 2 is 5. 5 divided by 2 is 2 after you chop off the 0.5. Is low greater than high? Yes, it is. So at this moment, we hit the base case. This if statement is true, and we are not calling the method mystery all over again like we were from here to here to here. So the number low, the value low in stack frame 3 is what the result is for this test case. Now this test case hinged on the fact that I put a 9 in here, and I'm the one who came up with these numbers up here. Maybe I need to redo all this with different numbers, or maybe I can just figure out what the answer is by looking at the available options. Are all the number of elements, is the number of elements in an array that are less than num, is that what the answer came out to be? Well, num was 9, and how many numbers are less than 9 in this sorted array? Yeah, 3. Hey, what a coincidence. 3 was the return value. That sounds good. Maybe you want to evaluate B through E just to rule them out, or maybe you'll just move on the exam since A seemed to satisfy this one test case. I'll let that up to you, or you could copy and paste all this code or type it into Eclipse and work with it and actually see the ingenious algorithm that's being used here. Moving on to the next page of the exam. We're here at questions number 11 and 12, and this is just a plain old logic error. There needs to be, we need to reset len count to 0. If you're looking for the longest string of consecutive numbers up here, let's see, 10 and 10, whoa, my string is up to 2. The length count is 2. 15, 15, 15, 15, the length count is 4. 10, 10, 10, the length count is 3. That's not more than 4. So each time that you find a new number, you go from the 15 to the 10, or the 10 to the 15, or the 7 to the 10, you need to reset len count back to 0 as part of this algorithm. Otherwise, it's a logic error. You'll see that on the next page here. In number 11, the problem that happens if you don't know that the answer to number 12, as I just kind of outlined, is E, the error that occurs logically is that instead of finding the longest string of or sequence of numbers, the value returned by this method actually just finds the number of occurrences of target. Whatever target is, it returns that number of values. Go ahead and trace the code, plug this in. Hopefully you'll see by insight that these were the wrong locations of len count equals 0. And hopefully you'll understand that if you trace the code from scratch, that currently without this fix down here, that the answer is C. Number 13. A lot of these questions are huge time sinks. You got to find patterns, you got to learn how to test things, and go with your intuition. Here, you might want to create an array, again, a small array of normal size. Here, the numbers can be in any order as described in the directions. So I just make up an array, and I hope that I can trace this code and come up with the right answer. Well, in this particular example, we have this imaginary number n that we're passing as a parameter up to num. And let's just say, n is 3. Let's plug in a 3 and see what happens. Well, if you do plug a 3 in, you'll see that this -1 gets returned. So the variable m ends up being -1. Now, if n is 1, when you analyze this code, you'll see that, actually, scratch that. I think I was going a little too quickly there, and I should not have waved this around so quickly. So, redoing a test case or two of this algorithm, let's just say that n is 15. N is equal to 15. And we run this code, where then, of course, num is 15. And k starts out at length -1, which would be a 5. And we look to see what's in position 5. It's also a 5. 5 is less than 15. That's true. And k is currently 5. So a 5 gets returned, and m ends up being 5. If I run the program with n being like a sort of a moderate number of, say, 6, then we get to a point where we're asking if k, which at that moment is 5, but the value of my stuff 5 is also a 5. Is 5 less than num? Is 5 less than 6? Yes, it is. So we again immediately return k. This whole method ends, and k, which is currently 5, returns, and that's what value gets stored in for m. So far, you may or may not be seeing a pattern. I keep testing this until I have the insight to see what algorithm is executing, or maybe I stop right here and try to rule out certain answers. One more time, I'm going to plug in another number. Let's go a little bit lower than 6. Let's go, say, to the value 2. If 2 is plugged in for n, that means m is also 2. We're starting k out at 5 again in this loop. My stuff 5 is also a 5. Is 5 less than 2? False. We go around the for loop again. We do not return k. K minus minus is down to this 4. And we're asking now if 8 is less than 2. False. And we're going to go around again. Is 4 less than 2? False. Is 1 less than 2? True. At the moment that we get to this 1, because at that point 1 will be less than 2, we return k, which is the actual index position where we found the thing that's less than the value num. So n is a special number, and when we get to something that's less than n, we stop and return that value. So that value m happens to be the spot in the array where if you look to the right of m plus 1, like up here at the 3 and higher, at n plus 1 is 3 and higher, all of those values to the right of n plus 1 out to the end of the array are greater than or equal to our original n. If your original n is a 2, all of these numbers are greater than 2. If your original number is 6, none of these numbers from any point in the right half are greater than 6. This 5 was not greater than 6. So only the numbers to the right of that spot are greater than 6. If you want to, you can test this a little bit further and plug in some numbers like, say, 0 or -1, and you'll see some other interesting things happening. And of course, you could always jumble up the numbers here in your array to really be able to tell. C is the answer, and my recommendation is to trace the code and look for patterns. Number 14, we have some modulus and another recursive method. And we start in stack frame 1 with the value x being equal to 1234. And because when you mod something, it immediately prints out there in that system out print. When you mod by 10, it peels off that ones digit. And there's no ln here, so it stays on the same line. And we do this, which is integer division, and that is not equal to 0. 123 is not equal to 0, so we do mystery x divided by 10. Well, x divided by 10 simplifies to 123. In other words, it chops off that 4, and now we call the method mystery again from within itself. It's recursive, and x in stack frame 2 is equal to 123, where you'll see that this 3 prints out, and we go to stack frame 2 then with the value x equals 12. Oops, stack frame number 3 I meant to say. Well, you already know the answer. The answer is, it starts with 4, 3. The answer is D. Moving on then to number 15. This is hard. You really have to know your rules on polymorphism. Veto.act. What the heck happens? Well, deep down he's an underdog, but he's referenced or cloaked as a dog. We'll see what that effect has. So here's the class underdog, and don't be confused with the overrided versions, well, the original versions in the base class of eat, not to be confused with the seed, and act, not to be confused with this act. So what happens? Well, when you execute this code right here, veto.act, we go to the act method, but which act method do we use? Well, you always use the act method, or in this case the eat method, in the child class. So this act executes first. But this line of code tells you, before you print the word sleep, it tells you first to go up to your superclass and execute its act method. So coming up here, this is what executes first in my output window, and the word run prints out, and it's a print, not a println, and then it calls eat. So before I come down here and system out print sleep, I have to do this eat. So which version executes? It's always the version in the deep down child class. So this eat tells you as the first line of code to call this eat, which tells you to print out eat with no spaces. Do we have a beat on the final answer yet? Nope. They gave us everything starts with run eat. So where am I? I just did this. I'm done with this method. I go back where I left, and I execute any code here because I'm done with this. Bark prints out next. Maybe I know what the final answer is. Maybe I don't. Yup, I'm finished. I don't even have to go any further. D is the answer because of that bark. But just for fun, let's now go back to where the eat was. Where was eat called from? Eat was called originally from here, and this act up here in the superclass was originally called from here. So we do still have a system out print sleep to execute, and sleep does print out at the very end. This is, of course, the answer that you see here circled, letter D. Number 16, more recursion. This method calls itself. And this is very easy. In stack frame number 1, n is equal to 5. And it ends up translating all that to 3 times the mystery of 4. It then calls itself again in stack frame 2 where n equals 4. We've done many worksheet questions like this. This M4 turns into another 3 times, but 3 times M3 because of this subtraction of 1 here. And it drills down to stack frame 3 and so on. It eventually hits the base case in stack frame 6 where n hits 0. And because of that 0, it returns a 1 at some point, but then it backtracks and it multiplies a whole bunch of 3s that were along for the ride. And it ends up, everything multiplies out to 3 to, I think it's the 5th power, 243. Number 17, another one having to do with arrays, a very weird algorithm that at first you might not recognize, but if you build a little array and throw some numbers in there, you will trace this and hopefully find the pattern. Let's ignore that. Tracing this code, knowing that when you divide by 2 it chops off the 0.5. Perhaps you run the code and you throw in a sample number. You'll see that location, in this case, starts out as the length of this divided by 2, which would be 2. The 5 divided by 2 is 2. K, of course, starts at 0 when you hit this loop. And then you're with this if statement, you're asking if the array value in position 0, which is a 3, is it greater than the array position, the array value found in location, which is 2. Is 3 greater than 4? No, it's not. So you k++, and you keep going, and you keep going, and you keep going until you're finished with this for loop. And it turns out, if you use this array right from the get-go, location 2 ends up being returned. In other words, this algorithm always returns the position of the largest value. It's guaranteed to work. That 10 was the biggest number, and its index position, I'm sorry, at some point location does become 1. I'm sorry, I did not trace this far enough. At some point this is true. It's true whenever at some point 10 is greater than 4. At that moment when 10 is greater than 4, at some point, maybe the 8's greater than 2. At some point, this location is 1. So the location of variable updates to 1, and it does return the index position of the largest value, which in this case would be this 1, because 10 is the largest value. Moving on, trace that code just to be sure. Number 18, very tricky. You have to know that strings are immutable. Here goes. S is the word world, and N is the value 6. Down here, and we'll just suppose the client program. Up here in the body of this method, the parameter X is equal to world, and the parameter Y is equal to 6, because they are being passed as parameters. Now what happens here? Well, this is string concatenation. We're taking the word world, we're gluing the word piece onto it. And because strings are immutable, as we've studied, this string x gets a whole new memory address in the memory of the computer. We'll call this like x sub 2. And world piece is stored there. And this x isn't really relevant anymore in the scope of things with this method changer. However, y being multiplied by 2, that does change the variable, the value 6 to a 12, and that 12 does overwrite the old value in y. Now that we're finished with this method and hit the curly brace, we come back here and we say, hey, what are the values of the two corresponding parameters that were passed up here? Well, guess what? Nothing changed down here. S is still world, n is still 6, the answer is A. This is only tricky if you think of it a different way. If this string were like a, say, a turtle object, and if up here, instead of concatenation, if you changed the color of the turtle to, say, green, when it was, we'll say, purple down here, then the change here would affect the change down here, and the answer would have been B. With normal kinds of objects, like turtle, many other things that we studied this semester. But strings are special. They act more like primitive variables, like an int or a double in a situation like this. So the answer is A. Number 19, a two-dimensional array with 3 rows and 4 columns is how you visualize this. And the length of mat is the number of, rows and columns. If it's got 3 rows and 4 columns, this is really represented as something that has 3 little mini arrays inside of one outer array. And the length of this is 3. So the length is the number of rows. And therefore, the length of this is a 3. This right here, if you go to a row 0 and find the length of this, if we put the right commas in there, it would be the length is 4. So this is really a 4. And now what happens in this double nested for loop? Well, it turns out anytime that row is equal to column, like the column number up here, if it's equal to the row number here, we're putting a 1 in there. So we definitely have 1s going down the diagonal where 1 is equal to 1. The intersection of 2 column and 2 row would be a 1. We definitely, because of this little slice right here, we are setting a 2 there, and this pattern comes up over and over again in computer science and especially the AP exam. And already I have a bead on the answer. The answer is D. And sorry about that. I wondered why I was wrong. The value is 2 that you're sticking in this array when the row is equal to the column. I should have put 2's here. And because of that, the answer D is very obvious. No other answer except for this one, and this one, and this one. So basically we just eliminated E. Now what else is happening in this algorithm? Well, if row is less than column, we're putting 1s in there. So anywhere where the 0 is less than like one of the columns, like this 0 is less than 1. So we need to put a 1 in there. Anywhere that 0 is less than, say, 2, we're putting a 1 in there. So apparently 1s end up in the upper right corner of our final answer. And that helps you narrow your answer down so that B and C are eliminated because they have 3's up there. And last of all, this is the wrong size. This is 4 rows and 3 columns, and not 3, 4, like our instantiated double two-dimensional array was. So A is eliminated for that reason. It's the wrong size, it's the wrong shape. So the answer is D. Moving on, notice I did not trace all of that code. I just looked for patterns. At number 20, we have some code here, and the only difference between these two methods, process 1 and process 2, is the version of the overloaded add method. Here there's an extra parameter called k, comma, and here there isn't. So the answer is A. They both work the same. The code's a little different, but when all of this code gets changed by the compiler into bytecode, it ends up working in the same binary hexadecimal code. In English, in source code, it might look different, but this turns into the same code as this. And as far as executing on your laptop computer or whatever you're using, it's the same result and the same amount of processing time. This does not slow the computer down at all.